All right, knowing what we know, both from this chapter, which hopefully was largely a little bit of a rejogging from what you'd learned in maybe the end of the Chem 108 course, but also then combining that with the knowledge of equilibria, specifically complexation equilibria and EDTA. I want to treat a more complicated cell. This comes out of your book, and I think it's a really good example. I do this in every class just because I think it ties things together really nicely. You're not probably going to see this exact type of thing on an exam or a quiz, but you'll see something similar where I combine probably a cell with some sort of equilibria, whether it's complexation or solubility or acids and bases or etc. It's really common, and that's because electrochemistry is the most common method to measure these equilibrium constants. So before I get ahead of myself, the question is asking you to look at this cell that's constructed here. So I pasted in the cartoon of the cell. And it is a cell that is used to determine Kf, the formation constant of mercury EDTA complex. So the cell is actually built to measure Kf indirectly. The right-hand cell compartment contains half a millimole of mercury 2 plus and 2 millimole of EDTA in a 0.1 liter buffered solution. It's buffered to pH 6. And then the voltage, the overall cell voltage in this cell is 0.342. And then what you have on the left cell that you can see is some hydrogen gas being bubbled in a tube over a solid platinum electrode. And this is what we call the standard hydrogen electrode. And so I mentioned before that we use this redox couple, 2H plus 2 electrons proceeds to make hydrogen gas. We say that has an E naught of 0 volts by convention and definition. We also call this standard reduction potential. If you can build it, if you can actually devise a cell where it exists, we call that the standard hydrogen electrode. Standard hydrogen electrode. Which often goes by its acronym SHE. Some people will call this the normal hydrogen electrode too, or NHE, and for our class those are the same. And so what you essentially have are two cells connected by a salt bridge. You have the standard hydrogen electrode half reaction, which is this, and really you actually don't have this, you have its reverse. You have H2 proceeds to H plus 2 electrons, and we know that because you're bubbling in hydrogen gas onto the platinum electrode, and then electrons are going to be running this way through the system. So you're actually oxidizing hydrogen gas. You don't have the H pluses here. And that's totally cool. Why? Because if we flip this reaction around from its original, it's still 0 volts by definition. So it doesn't matter how you construct this. This is still going to be a 0 volt, a standard hydrogen electrode, as long as the pressure on this hydrogen is 1 atmosphere, which we'll just assume that it is here. So other complicated things about this cell. Look at the right cell. This looks a little weird. You've got liquid mercury, which is liquid at below 0, so it's molten in most atmospheric settings or all atmospheric settings. And you've got a platinum wire that actually contacts the mercury. So the actual electrode that's in contact with solution here is not platinum, it's mercury. So you got liquid mercury metal as the electrode, and then in that solution you've got mercury 2 plus and some EDTA. And so you've got mercury 0 here, because that's the elemental state of mercury, is 0 valent form, and then you got mercury 2 plus floating around and some EDTA, and you have volumes of each of these things. Or you have the actual moles up here per volume, so we could compute the concentrations. They give us the cell. We could have deduced this ourselves, but we'll draw the cell up just so that we have it. And remember, the way that these cell conventions work is electrons are always flowing left to right. And so we know that because SHE is on the left here, we knew that that thing had to be getting oxidized, which we deduced already, but it is. The hydrogen's being oxidized in this direction. Electrons then are being liberated through the wire, and then they're being dumped into the mercury, and then mercury, liquid mercury, is giving those off to something in the solution, and it looks like probably mercury 2+ because it's the only ion that's redox active in the system. So what we have, we write this up, we have SHE, which, you know, to write this out specifically, if I were to write this out as the full cell, what this would really look like would be platinum solid as the first electrode. We'd have the vertical line, which would denote the fact that we have a phase boundary there. That platinum electrode then is in contact with hydrogen gas. So I would write this out, which, you know, we could write this a couple different ways, but probably I would write this out as PH2 gas, and then I would write 1 atm in parentheses, and then I would write a comma here, and because it's SHE, by definition what that also means is it has to be 1 atm of gas, and it has to also be 1 molar of protons. So it'd probably be something like HCl, aqueous, or it could be any strong acid that is essentially protons at 1 molar. And then that is in contact, so that's the whole solution on this side. That's our SHE electrode, which then goes to the salt bridge. So this whole thing here is SHE. So I'm just writing out this to be a little bit more clear what the heck that actually means. But hopefully it makes sense now. We've got platinum, and then in equilibrium on the platinum, we have 1 atmosphere of hydrogen, and we have 1 molar H+. Those are 1 molar each, which sets that potential to 0 volts by definition when it's standard. And it's standard because they're 1 on both of these. So that's our 0 volt side on our SHE, and then move through the salt bridge. The next thing we encounter is the next solution, which contains the complex here, which we'll get to in a second. I'll do this in blue. So we've got our mercury EDTA complex, which is the equivalent here of mercury Y2- that we talked about in the complexation chapter. And we know that is going to be true. We know at least some amount is going to be complex just because we're adding mercury 2+ and EDTA to the solution. They're being generous, and they computed for us what the concentrations of each of those things are and what amount of it is going to be complex. That's not hard math. That's literally just figuring out how many moles of EDTA, which one's the limiting reagent, which one's going to be the thing that gets that runs out in terms of the complexation. And then we know that there's going to be some amount of EDTA, and actually this should be 0.00500 molar. Just because I'm running out of room, I'm going to put it up here. This is EDTA, aqueous, which is at 0.0150 molar, and that's it in solution. Those are technically what we have in the solution, and then the final phase boundary here will be mercury liquid. And if you want to be really obvious and clear here, then you would also write then platinum here, solid, because the platinum is actually in contact with mercury, and there's a phase boundary there between the liquid and the solid, though this won't actually matter in terms of the full cell, so that's why it's left out in the cartoon here. So we got a complicated cell, right? We've got our standard hydrogen electrode over here, which actually is the easy part, because even though it looks weird, everything's well defined, and so we're not going to have to worry about that one much. It's this side that is the side that sometimes we'll call the indicator side, or the working side, because this is where the action's taking place, and it's the change on this side that's dictating ultimately the overall E cell. Because if you think about it, the overall, or not the E cell, not the standard E cell, but the real E cell, the overall E cell is really just a voltage difference between these two half cells, right? That's what E cell is in this case. And in this case, SHE is 0 volts. So it's all this stuff on this side that's dictating what the overall cell potential change is. What's nice is they gave us that as positive 0.342 in the orientation that it's being measured in. So we somehow have to backtrack with E cell to get to Kf, which is the equilibrium constant. It's going to be easier than you think, I promise, once I set it up. So first thing we need to do is just write out the half reactions. What is being oxidized and what is being reduced? We know, because we already talked about it, that the hydrogen gas is being reduced in the system. So that's, or not the hydrogen gas is being oxidized in the system to H+. And so what we can write out then, because we're going to write these both as reduction reactions, what we can do is write out we can write it out as a reduction reaction, even though we know that hydrogen is actually proceeding to 2H plus 2 electrons being oxidized. Even though we know that, I'm going to write it out just because that allows us to look up our standard reduction potential. So we've got 2 protons plus 2 electrons makes H2. It's not the direction that it's actually occurring, but that's okay. We're just going to start there. What do we have in the other cell? Well, know that we added, we have mercury 2+ in there, and we have mercury 0. Those are the only 2 redox active things in the system. So as a reduction, that's going to look like mercury 2+ plus 2 electrons makes mercury 0. So those are the 2 half reactions. Of course, mercury is also participating in its own complexation reaction with EDTA, but that's not important right now because we're just thinking about what's contributing to the cell potential, which are the relative concentrations of these things if they're input into a Nernst equation. Of course, that mercury concentration is going to be a function of the EDTA in the system, but that's what we're going to back out to. So I'll look up the standard reduction potentials for both of these half reactions. You can see one I just wrote down here. It's 0.852, and we know the other is 0 by definition. And so I'm going to arrange these in the way that they're actually occurring in real life. And we know that the hydrogen reaction is occurring in the opposite direction. So sort of by default, we know then that the mercury is going in the correct direction. So what that means then is I need to multiply this reaction by -1, so we need to flip it, which means I need to multiply this by -1, which doesn't change anything. So I'll add these 2 reactions down, and what we get is positive 0.852, and we get a full cell reaction then of mercury 2+ plus hydrogen gas proceeds to make 2 protons plus mercury 0, and I'm leaving out the phase states here just because I'm saving myself room. And so our standard E cell is equal to positive 0.852 for this, so assuming everything is at 1 molar, of course. Okay, so second step then is to write up our actual E cell, which is a function of our E naught cell, but takes into consideration the specific concentrations as they pertain to the Nernst equation. And we are given specific concentrations simply because we have the moles of each of these things, and then we have the moles of excess, in this case of EDTA. So we assumed that the limiting reagent here was mercury 2+, which gave rise to complexing all of it out in the form of EDTA. We know that just because Kf is so large for virtually all ions. And then whatever excess EDTA we had in solution, that gives rise to the 0.150 molar. And then we know that we're going to have a trickle of mercury in the system, but it's going to be tiny, 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 which we will evaluate here in a second. So our E cell then is going to be equal to our E naught cell, and then that's going to be minus, and we're just assuming this is all done at 25C because it wasn't indicated otherwise, so we use the shorthand version, so 0.5916 over n in this case being 2 electrons. This is log base 10, and then we have the equilibrium expression part, which is going to be the concentration of the products over the reactants. So we need to be a little bit careful here. So we're talking about this full cell reaction here. So that would mean we have the concentration of H plus, but be careful because that has a coefficient of 2, so that gets squared. We do not treat mercury because that's a pure substance, that's a liquid, pure substance, so nothing else in the numerator in this case. And then in the denominator we have mercury 2 plus ion, and then we have the pressure of hydrogen gas down here. So anytime you have gases, we're talking about pressures of those things. That's true in all equilibrium equations, which I talked about in chapter 6 video. Okay, so this is our full cell equation. There's a couple things that we can do here. One is that because we're told that this is SHE, this is a standard hydrogen electrode, what that has to mean is that the concentration of H plus is 1 molar and that the pressure of hydrogen gas is 1 atmosphere. So 1 squared is 1, and pressure being 1, that this simplifies to 1 over the mercury equation. So let me rewrite this then as E cell equals 0.852 was the value that we computed here for E cell, minus 0.5916 over 2 log 10 1 over mercury ion concentration. Cool. And we have the measured E cell to actually be 0.342. So let me erase this and be more explicit. This is 0.342. So the only thing that we do not have solved in this system is the free mercury concentration, which is going to be necessary because we have the complex conformation, we have the EDTA concentration, and once we have mercury, then we have all of the species that go into computing the KF, which is what we're trying to do here. So we go through this, and we can solve this. Let me put this into my calculator really quick. Okay, so compute that. Be careful again because you've got mixed operations here. So what I did was just subtracted the 0.852 from the 0.342 first, and then I multiplied this by 2 over 0.05916. I multiplied the left side of the equation by that, and then took that value. That gives you 17.2414, and then take 10 to that to get rid of the log term, and then take the reciprocal of that, and we get a concentration of very, very tiny, right? 5.736 times 10 to the minus 18 molar. So let's take a moment just to understand what that means, right? You, by setting up this cell, which is a fairly simple cell to set up, I wouldn't say simple, this is a moderate cell to set up, but it would take me an hour to set this thing up. What you've done is actually used a macroscopic voltage, which is, remember, a proxy for the chemical potential of the system. You measured this thing with a multimeter that you buy at the hardware store. Easy to do. You get a voltage. It's easy to read. And what that voltage actually is telling you is the concentration of mercury in a solution at 10 to the minus 18 molar. Think about that for a second. We're talking about, I don't even know the prefix in 10 to the minus 18. That's like attomolar maybe. Femto, I think, is 10 to the minus 15. So pico is 12, femto is 15. I think atto is 18. So you're talking about 5 attomolar as the concentration that you're measuring here. Tiny, tiny, tiny amounts of mercury in solution, measured with a device that you can buy in a hardware store. That's the power of electrochemistry. So anyway, we have that value. Now we can take that value in conjunction with these two other values to extract our formation constant Kf. So let me erase some of this stuff. Okay, so our final step is one, hopefully that's pretty familiar. It hasn't been that long. So we just need to compute the Kf. And as I mentioned, you know, all of the complexation equilibria for EDTA, the convention is always going to be metal ion plus the Y4 minus version of the EDTA to form that complex. And in this case, we're actually given the concentration of the complex, the excess amount of EDTA, and we just computed the concentration for mercury being that small value, 10 to the minus 18. We don't technically have Y4 minus concentration, but that's easy to get because remember the Y4 minus concentration is simply the EDTA concentration multiplied by whatever the fraction it is in at the pH. We're told that this whole thing is sitting at pH 6, and so the last thing we need here is this table there, which tells us that at pH 6 the fraction of Y4 minus present is 1.8 times 10 to the minus 5. So to get to Y4 minus, then we would take our excess EDTA concentration, which is 0.0150 molar, and then multiply that by 1.8 times 10 to the minus 5. And let's see if I have computed that. That I don't have, but we'll plug this value in here in a second. Okay, that gives us a value of 2.7 times 10 to the minus 7. So we know Y4 minus now, at least at that pH. We know the concentration of mercury 2 plus, which is this tiny value we just computed in the previous step, and then we know the concentration of the complex, which is 0.005 molar. We could have computed that too if they didn't give it to us, just simply based on the solution that they gave us and the limiting reagent being mercury in this case. Plug all those values in, and we compute a Kf value of 3 times 10 to the 21st, so a really large value. This is how Kf values are computed using electrochemistry, because it's a really straightforward way, and as long as you have multimeters that can measure out to, in this case it's only 3 digits, but we can get multimeters that measure out, we can get these precision multimeters that measure out to like 6 or 7 sig figs, and as long as we know our solutions to that degree of precision as well, our concentrations, then we can compute Kf's with a high degree of accuracy. In this case, we're only keeping 1 sig fig. I should note that this is Kf and not, this is not K prime F, because remember, if we wanted to compute K prime F, then we would have needed to multiply this by our alpha coefficient. Because here, what we essentially did was normally here, this is Y4 minus times alpha Y4 minus, or I'm sorry, EDTA times alpha Y4 minus, and then we divide or multiply that into the Kf value to get the conditional Kf without changing the equilibrium. Here we actually just changed the equilibrium deliberately and computed the Y4 minus. So this, in this case, this is just the regular Kf value.